A very good day to all the participants. Today we are going to discuss about the power station pumps and pumping systems. It will be done in 4 phases. First we will discuss about the types of pumps, then pumping system and their arrangements, then assessment of pumps, and subsequently at last energy efficiency opportunities in operation of pumps. So let us start. In power station, we have several types of pumps, particularly not only water pumps, ash slurry and other material also handled by pumps. So we have condensate extraction pumps, boiler feed pump, DM water storage pump, makeup water pump, HP water pumps, ash slurry pumps, air conditioning plant pumps, cooling tower pumps, CW pumps, booster pumps, water pumps for raw water supply, service water supply, firefighting arrangement, fuel oil. Pumps can be classified according to their operating principle. So these are the types of pumps, service conditions, and how they are constructed. In general, we find two categories, major categories: dynamic type and positive displacement type. Dynamic means it may be centrifugal or special type of pumps, and positive displacement may be rotary or reciprocating. In rotary, we may have internal gearing type pumps or external gearing type pumps, lobe pumps or sliding vane pumps. So in other pattern, we can arrange this pump classification as positive displacement pump and centrifugal pump. Positive displacement pump may be rotary, that may be distributed further in 4 classes: gear pump, lobe pump, vane pump and screw pump. And reciprocating pumps may be piston type, plunger type and diaphragm type. Now the centrifugal pumps, they are having volute casing and ring sections, barrel casing. They may be radial flow, axial flow or mixed flow. Gear pumps may be externally emitting gears arranged in such a way they will continue to suck the liquid and discharge the liquid, or they may be arranged in such a way that just like planetary gear, one gear is placed inside the external gear. So in that way this may be internal gear pumping arrangement. Lobe pumps are utilized for supplying acid and alkali. Their two lobes are mating with each other and they are sucking the liquid continuously along the axis and discharging axially the fluid through a chamber, sealed chamber. They are placed in 2 shafts. One is driving shaft, another is driven shaft. The driving shaft and driven shaft both are supported with bearings, and there is a compact sealing arrangement. These type of pumps are specifically used for the purpose of transfer of acid or alkali, as these pumps are very smooth in operation. Vane pumps are special type of pumps where vane impeller blades, they are sliding type, the spring loaded, and the entire impeller is placed eccentrically. So there is a continuous suction and the vane continuously move the liquid along the casing and then discharge it along the discharge duct. So this way vane pumps are used particularly for slurry and other purposes. Screw pumps are special type of pumps where we have 2 screws or 3 screws fitted within the casing in such a way there may be one driving screw and other are driven screw, and when these screws rotate, so naturally the fluid sucked across the screw axially, and then this fluid is discharged from the end of the transmission path through discharge duct. So there is an axial suction and radial discharge across the screw. Pistons are reciprocating type of pumps which are fitted with a piston cylinder arrangement along with non-return type suction and discharge valve. The suction and discharge valves are placed in such a way when one is open, another is closed, and it may be single acting or double acting, and depending upon the configuration there may be a duplex type or single type arrangement to operate it. Plunger pumps are another type of piston cylinder type of arranged pumps which are used either double plunger type or single plunger type. They are attached with a crankshaft arrangement which is continuously reciprocating and sucking the fluid and discharging the liquid. These type of pumps are mostly used in HP chemical dosing purpose wherever it is available. Diaphragm pumps are another type of positive displacement pump which are used for sucking and disposing high density slurry or some other liquid. These are utilized at very slow speed operation because it is handling high density fluid, and they are having a non-return type of suction and discharge valves, and there is a diaphragm which is continuously moved to impart energy within the fluid which is getting transmitted. In centrifugal pumps, we use a casing which is shaped like involute, and as a result of that there may be continuous suction, pressurization, imparting of energy within the fluid, and then discharge of the fluid at a higher pressure and velocity. So this way centrifugal pump casing is made. There may be single suction type volute casing or double suction type volute casing. In high capacity centrifugal pumps, we use number of sections or stages to increase the capacity of discharge. So here ring sections are made with single impeller and a casing part, involute casing part with the cage, and as we go on adding these ring sections, the pump capacity increases. In high capacity and high temperature application of pumps, we find that these stages or ring sections of the pumping is encased within a barrel. So these barrels are splitted across the horizontal section and they are clamped together, bolted together. So this is called barrel casing. Mostly HP heaters or high pressure HP boiler feed pumps and high pressure pumps, we use it. According to flow pattern, pump can be classified into three categories: radial flow, axial flow or mixed flow. In radial flow, pumps are sucking the liquid along the axis and discharging it radially. There may be single inlet or double inlet type. That means suction may be taking from one side or suction may be taking from both sides. If it is from both sides, the thrust balancing is better. Axial flow pumps are fitted with axial flow type impellers. These impellers suck the liquid along the axis and discharge it along the axis. So that's why these type of pumps are called axial flow pumps. In mixed flow pumps, the suction is though along the axis, the discharge is neither completely radial or nor axial. That's why it is called a mixed flow arrangement. The impellers are such that they turn around the flow passage, flow quantity along the direction at the maximum capacity. Mostly in CW pumping and CEP, we find this kind of arrangements. So, positive displacement pumps are the pumps which are positively displacing the liquid along the direction of flow through the pumps. There is a fixed amount of liquid taken from one end and discharged positively to other end. If these pumps are blocked, there may be pressure rise and it can damage the pumps. So positive displacement pumps may be reciprocating type or rotary type. Reciprocating types pumps are having either piston cylinder or plunger type arrangement with crankshaft, and in case of rotary pumps we have vane or gear or cam, and both these types of pumps are utilized for high density viscous fluid transfer. Centrifugal pumps are dynamic category pumps which are actually having rotating impellers which convert the kinetic energy of the fluid increased into the pressure and velocity head at the discharge of the pump. Thereby pump is sending the fluid across the pump. There are two types of pumping devices, and in the centrifugal there may be double inlet types and single inlet type. Discharge may be axial or radial or mixed type. So construction wise, in the centrifugal pump we have volute casing, rotating impeller and vanes within the casing. There is a suction and discharge duct. So liquid is forced into the impeller and the vanes pass the kinetic energy into the liquid. Liquid rotates and leaves the impeller, and due to the movement through the volute casing, the kinetic energy inside the liquid that is converted into two heads. Pressure is increasing and velocity is also increasing. However, increase in pressure is more than the velocity. The energy input in the impeller is getting converted into velocity head and pressure head. Velocity is actually decreases when the movement of fluid takes place across the impeller to casing, and pressure head increases when the movement of fluid takes place from impeller to casing due to the impact of the vanes. In centrifugal pumps, impeller and shaft is key fitted, therefore they are rotating together, and casing, volute casing and bearings are supporting this shaft, and impeller is within the volute casing. Suction is taking place axially and discharge is radially, where there is a radial flow arrangement. There is shaft balancing arrangement by some thrust collar, and there is also arrangement to prevent any leakage from the bearing side. That's why oil rings are there. Through these oil rings and support arrangement, we prevent any leakage of lubricating oil. A centrifugal pump is one of the simplest piece of equipment in any process plant. Liquid is forced into an impeller either by atmospheric pressure or, in case of a jet pump, by artificial pressure. The vanes of impeller pass kinetic energy to the liquid and therefore causing the liquid to rotate, and liquid leaves the impeller at high velocity. The impeller is surrounded by a volute casing, or in case of turbine pump, a stationary diffuser ring is also available. The volute or stationary diffuser ring converts the kinetic energy into pressure energy, and in case of the impeller, if you see, this impeller is a circular metallic disc, and it has a built-in passage for the flow of fluid. Impellers are generally made of either bronze or cast iron or stainless steel, but sometimes we use also polycarbonate materials for anti-corrosive use. Now, number of impeller uh, that is given in a system is determined by the number of stages of the pump. A single stage pump has one impeller, and for low head that is given, it may have single suction arrangement or double suction arrangement. But for multiple stages, impellers are determined by number of stages. If number of stages are 5, we find 5 numbers of impellers. Now, impellers are classified on the basis of direction of flow from the rotational axis. Suction type may be single suction or double suction, shape of or mechanical construction. Closed impeller have vane enclosed by shrouds, and open and semi-open impellers we have vortex pump impellers that depending upon the configuration we have different either open type or closed type impeller. Shaft is attached to the impeller, and this shaft is transferring torque which it is receiving from the motor, as the shaft is coupled with the motor, and that is running the pump. The function of the casing is to convert the kinetic energy imparted by the impeller into the fluid into velocity and pressure head, and it is actually encasing the impeller in such a way that it is smoothly converting into pressure and velocity head according to the space provided. Casing may be volute type, which is mostly found in single stage, double inlet or single inlet pumps, or maybe circular type. Circular types actually in multi-stage pumps we find circular type casing. There in each stage actually casing is having vanes surrounding the impeller which are converting this kinetic energy into velocity and pressure and sending it to second stage of typically boiler feed pump is the major power consuming pump in all the installations pumps installed in a power plant. It consumes almost 20% of the total auxiliary power consumption in the power station. So basically for a 210 megawatt unit, two types of BFPs are available. One consumes around 4 megawatt of power and delivers at a rate of 430 tons per hour. Another consumes 3.5 megawatt power and delivers around 398 tons per hour. And both are running at a very high RPM. RPM is the key parameter that shows the pump's size and other things, and how they are consuming power to give so much discharge head to send the water into the boiler. As such, all the pumps can be specified or defined as a volumetric machine to deliver liquid fluid at a rated capacity at a given temperature and pressure. So it is just like fans handling the gaseous fluid, it is handling the liquid fluid, and both are volumetric machine. Now let us try to understand the pumping systems. In fact, pumping systems are almost part and parcel of any process or manufacturing or product industry. Everywhere, wherever we find a fluid flow, liquid flow, and it requires a transfer of liquid from one place to another, we have a pump and pumping system. Almost 20% of the world's electrical energy demand is due to pumping system, and it may be used for domestic, commercial, industrial or agricultural services, even for disposal of municipal waste. So naturally the requirement of pumping system is not only to transfer liquid, it is also to circulate liquid around the system where we need a transfer from one source to another location to store, and from there to reclaim back to another place according to the requirement. The main components of a pumping systems are pumps, prime movers. Prime movers may be electric motors, diesel engines, or air pneumatic systems. Connecting pipings to carry the fluid and take in the fluid. Valves to control flow and isolate flow. Other fittings, controls, and instrumentations. We may have some end-use equipments which have different requirements like pressure, flow. Therefore, the pumping system components and configurations are determined by these end-use equipments like heat exchangers, tanks, and hydraulic machines. Every fluid flow system imparts a system resistance across the fluid flow passage, and pressure is needed to pump the liquid through the system at a certain rate to overcome this system resistance. This pressure has to be high enough to overcome the resistance of the system, and which is also called the head. Now, the total head is the sum of static head and friction head. Static head is the difference in height between the source and the destination of the liquid locations where it is stored and the source, and it is independent of the flow rate. It is static head is actually a constant parameter. Static head consists of static suction head, that is resulting from the lifting the liquid relative to the pump center line, and it is positive if the liquid level is above the pump center line, and negative if the liquid level is below pump center line. And if it is negative, sometimes it is also called suction lift. And static discharge head, that is the vertical distance between the pump center line and the surface of the liquid in the destination tank. So static head at a certain pressure depends on the weight of the liquid and can be calculated as the given in the formula, that head in feet, pressure in psi multiplied by 2.31 divided by specific gravity of the liquid. Now let us try to understand the friction head or head loss due to friction in the flow passage. This is the loss needed to overcome that is caused by the resistance to the flow in the pipe and fittings, and it is also dependent upon the conduit of the flow passage, its geometrical configuration, number of bends, etc. So size, condition, type of pipe, number and type of pipe fittings, flow rate, nature of liquid, everything comes into this creation of friction head. It is proportional to the square of the flow rate, and a closed loop circulating system only exhibit friction head. There is no static head. In most of the cases, the total head of a system is a combination of static head and friction head, and left side of this figure shows a system with high static head. That means destination reservoir is much higher than the source, and right hand side the figure shows a low static head, maybe destination at the ground level and not much higher than the source from where it is pumped. So we find system head has got three components against which a pump has to deliver liquid. It constitutes the static head difference between the suction tank to delivery tank, then tank's pressure head difference, and friction head in suction to delivery piping. So these three components together constitutes system head. The head and the flow rate determine the performance of a pump, that is shown in this figure. So as the that is also called performance curve of a pump or pump characteristics curve. So it is a showing that how the head is gradually decreasing with increasing flow. So as the resistance of a system increases, the head will also increase. So this in turn causes the flow rate to decrease and will eventually reach to zero. A zero flow rate is only acceptable for a short period without causing the pump to stop working and burn out, churning. Now let us try to understand the system head and how it is configured with the capacity utilization of the pump. System head is a combination of static head, pressure head and friction head. But it has to be remembered that static and pressure head, they together remain constant with capacity utilization, but friction head components varies with the square of the velocity of the liquid in the flow passages. So more is the flow, more will be the friction head, and that will create more head requirement for delivery of liquid at a desired capacity. Let us now try to understand the head developed by a pump. For delivering the liquid in the system, pump has to impart energy to the liquid. So this is measured by the difference between the discharge head at the delivery end and suction head at the inlet end of the pump. So pressure head difference plus velocity head difference gives the pump head. Okay. And therefore, with respect to flow rate through the pump, the head developed by the pump must be equal to the system head. System head means static head, velocity head and friction head. So we get static head and pressure head and friction head equal to, that means system head must be equal to the pump head developed by the pump to make a flow at a particular rate. Now let us try to understand the operating characteristics. Whenever we employ a pump for a particular purpose, we know what is the rate of flow required for that purpose. So knowing the flow requirement, we choose the pump, select the pump to get available pump head which will be matching with the system head, and so we will get the availability of fluid flow at a best efficiency point. And these curves are showing that head versus capacity, power versus capacity and efficiency versus capacity, which shows that we must choose the pump in such a way that we can utilize it at maximum efficiency point and utilize it at maximum capacity for the purpose of transfer of fluid. So rate of flow through a pump at a certain head is called the duty point, and the pump performance curves are made up with many duty points. The pump operating point is determined by the intersection of the system curve and the pump curve. So as found in the figure. Now the best efficiency point is the pumping capacity at maximum impeller diameter, or rather at which efficiency of pump is at the maximum level. So any point where the system curve meets with the pump with respect to flow before or after is definitely not the best efficiency point. So we have to choose the pump, select the pump accordingly so that we get the maximum efficiency. Now we can alter the pump operating point depending upon the requirement of flow. If we want to reduce the flow, then as we see in the HQ curve, we can head developed by the pump can be reduced by speed control or we can throttle through a valve which will increase the system resistance. So this way it can be, flow can be reduced. Similarly, if we want to increase the flow, we can increase the head developed by the pump by increasing the RPM. So that way the flow will be more, system resistance will cut at a later part with the head developed pump operating curve. So naturally this way you can control the operating point of a pump with respect to system resistance and thereby control the flow. Now pump efficiency calculation, for that one thing is that pump hydraulic power. This can be calculated with respect to WQH equal to this pump hydraulic power in kilowatt. W is weight density of water, Q is the flow rate in meter per second, H is the head generated by pump in meter. A combination multiplying these three factors we get pump hydraulic power. Then pump input power is cube root VI cos phi square root 3 VI cos phi motor efficiency, and pump efficiency is pump water power divided by pump input power. So this way we can calculate the pump efficiency. Now we are coming to a very important parameter which is called NPSH, net positive suction head. Now it has got two way it is represented. The net positive suction head available indicates how much the pump suction exceeds the liquid vapor pressure, and it is characteristics of the system design. And NPSH required is the pump suction needed to avoid cavitation in a pump, and that is a characteristics of pump design. So naturally NPSH available is the energy at the inlet of the pump that can be utilized to get the flow of liquid through the suction piping and up to the pump into the impeller, and it is represented by total suction head minus the vapor pressure of the liquid at the pumping temperature. And it can be represented also by equation, and so at any point the pressure of the suction line of the pressure of the liquid in the suction line never be reduced to vapor pressure of the liquid, so that there may be any chance of cavitation in the pump due to absence of liquid. And now NPSH required, that is a function of the pump design. So minimum required margin between suction head and vapor pressure must be given so that there is no chance of cavitation and fail of NPSH available for the proper flow arrangement. So NPSH available to the pump is the suction head available over and above the vapor pressure of the liquid, and after subtracting the friction losses. So this way NPSH available can be calculated, and it has to be seen that NPSH required can be maintained in such a way that is within control. For cavitation free operation of pumps, NPSH available must be greater than NPSH required with at least some margin, and this margin is necessary between NPSH available and NPSH required, and it may reduce and lead to cavitation when we have increase in capacity utilization of pump above design value, increase in liquid temperature, so there is more vapor pressure, and increase in losses due to choke up or restriction in suction piping, that is creating more losses, frictional resistance, so that is reducing the NPSH available. Let us now try to understand the effect of unavailability of NPSH. As we know that cavitation or vaporization is the formation of bubbles inside the pump, and this may occur when at the fluid's local static pressure, that is becoming lower than the liquid's vapor pressure at the operating temperature inside the pump. So possible cause is when the fluid accelerates in a control valve or in a pump impeller, then may cavitation takes place with the unavailability of NPSH. Vaporization itself does not cause any damage, but when the velocity is decreased and pressure increased in the process of liquid imparting the kinetic energy conversion is taking place, and there is more of velocity, pressure creation, and vapor will then definitely evaporate and collapse. So this will create damage mechanism in terms of erosion of vane surfaces due to increase in there may be increase in noise and vibration, and there may be partial chokage of the impeller passage that may reduce the pump performance, and that may in extreme case there may be total loss of head. So all these things may happen with unavailability of required NPSH, that is not being met with available NPSH. In case of positive suction system, pump draws the liquid from the suction tank located above the pump level, like boiler feed pump, CEP, CW system, and as a result these pumps are always giving a suction head in a positive suction head at the pump inlet. When we are drawing water or liquid from a sump with a foot valve, in that case it is a negative suction system, and liquid is lifted by the pump from the suction well located below the level of the pump. So this type of arrangement mostly in agricultural pumps and wet pit pumps are negative suction type arrangement. Let us try to understand the process of assessment of pump performance. The work performed by a pump is a function of the total head and the weight of the liquid pumped in a given time. Now pump's shaft power is the actual horsepower delivered by the pump shaft, and it is calculated as hydraulic power divided by pump efficiency. Now pump efficiency, naturally it will be hydraulic power by pump shaft power. Now pump output or water horsepower or hydraulic horsepower, whatever may be called, is the liquid horsepower delivered by the pump and can be calculated as hydraulic power equal to Q into HD minus HS into rho into G, where Q you know it is the flow rate, HD is the discharge head, HS is the suction head, rho is the density of the fluid, and G equal to acceleration due to gravity. So this way you can evaluate the pump hydraulic power. There are certain practical difficulties in assessing the pump performance. If we do not have the pump specification data like performance curves, and most companies do not keep the original equipment manufacturers document that provide these data. So naturally how the pump is loaded and how the pump flow is calibrated with reference to the head across the flow passage. So naturally it is only estimated and accordingly it is modified or taken care of. Then flow measurement difficulties are there. Not always we find everywhere we have a flow meter to assess the flow taking place in various locations. We have improper calibration of pressure gauge and measuring instruments. Temperatures are not always measured across the flow passages. So all these difficulties can give rise to difficulty in assessing the pump performance. Now we'll try to understand the factors those affect the pump performance and getting the optimum efficiency, and where we can conserve the energy. The main areas of having the optimization of energy consumption of a pump, that includes with selection of right pump with size and speed, controlling the flow rate by speed variation, pumps in parallel to meet varying demand, eliminating the flow control valves or bypass control system, start and stop control of pump or impeller trimming. So all these methods can effectively give energy efficient operation of pumping systems. Selecting a right pump typically start with the proper choice of size and speed of the pump. As the figure shows that we require a original equipment manufacturer supplied pump performance curve, and this is for a centrifugal pump with a characteristics for clear water as the pumping liquid. Now in selecting the pump, supplier try to match the system curve supplied by the user with a pump curve that satisfy these needs as closely as possible. Now operating point is where the system curve and pump performance curve intersect. We have already discussed about that, but our interest is on the best efficiency point, which is the pumping capacity at maximum impeller diameter that will be given as per system requirement. So best efficiency point should be matched with reference to system head, and all the points right or left of the best efficiency point are having lower efficiency, and accordingly we have to choose the fan size and speed. Now best efficiency point is affected when the selected pump is oversized. The reason is the flow of oversized pump must be controlled with different other methods, either throttling or bypass arrangement, and these provide additional system resistance by increasing the friction in the flow passage. Thereby we are changing the system resistance or system head requirement. As a result, the system curve shifts to the left and intersects the pump curve at another point, that means lower flow rate. So best efficiency point is getting lowered, and in that way pump efficiency is getting reduced, and flow through the pump is also getting reduced, but power consumption is not getting reduced. That has to be remembered. So that's why oversized pumps can create inefficiencies, and to overcome that we have to give the variable speed drives or two-speed drives, lower RPM, smaller impeller or trimmed impeller. This can reduce the system load. I mean they are not changing the system resistance, but they are changing the pump performance curve and thereby reducing the total capacity control of the flow. Now for centrifugal pumps, rotating impeller generates the head, and impeller peripheral velocity is directly related to shaft rotational speed or RPM. Therefore, varying the rotational speed of the shaft directly affect the performance of the pump. So flow rate, head, power, these performance parameters can be changed with varying the rotating speed. So at different speeds, if we run the pump, we get that flow rate is proportional to the rotating speed, head developed is proportional to the square of the rotating speed, and power requirement is proportional to the cube of the rotating speed. So naturally it is more efficient, effective and conserving the energy. So we find that controlling the pump speed is the most efficient way to control the flow, because when the pump speed is reduced, the power consumption is also getting reduced. Now, most commonly used method to reduce pump speed is variable speed drive. Now, variable speed drive allow pump to go for speed adjustment over a continuous range and avoiding the need to jump from one speed to another with just like multiple speed pumps. And variable speed drive control pump speed, it may be by two types of system. Mechanical variable speed drives include hydraulic clutches, fluid couplings and adjustable belt and pulleys, and electrical variable speed drives include eddy current clutches, wound rotor motor controllers, variable frequency drives, and VFDs are most popular and adjust the electrical frequency of the power supplied to a motor to change the motor RPM. So this way you can utilize them. In this figure we will try to understand how the speed control is actually working. Suppose a pump is running at high speed N1 giving a flow of Q1, and when this discharge valve is wide open and it is running at N1 speed. Now if we reduce the speed to N2, so naturally with the speed coming to N2 which is reduced, as a result the system resistance curve or system head is cut at a lower value of capacity utilization Q2. So naturally with valve wide open we are getting a reduced flow from Q1 to Q2 without any excess head utilization. So head requirement with the speed has also reduced as a result. So as the RPM reduced, head reduced, so power consumption is also getting reduced. So that's why it is always better to have variable speed drive. Parallel operation is one of the improvement methods for varying demand meeting operation. So when we are operating two or more pumps in parallel, then the quantity of flow rate is gradually building up without changing the head. So naturally when the demand is lower we are running with a single pump. When demand is increasing we are running more pumps in parallel. So naturally pump curves for single pump, two pump or three pumps in parallel, they are actually adding up the flow rate, but system resistance or system curve is not changing. Naturally we are getting more flow across the system and discharge head remains same. When head requirement is more and when we have a chance of going for available NPSH which is very close proximity to required NPSH, then we use series pumping arrangement. Just like we have booster pump before boiler feed pump, or some places we have pumps in series, so that we can build up the head without changing the flow capacity. So this way when series pumping is arranged, flow is remaining constant but head developed in successive pump is more, and that is improving the discharge capacity at a higher pressure. So another method of control of flow is by flow control by closing or opening the discharge valve, or which is also known as throttle control arrangement. Now this method reduces the flow, but this is not advantageous because it does not reduce the power consumption, as the total head required by the system due to frictional resistance increases, and as we find that this is actually when the valve is half closed or open. So there is a throttling, is a loss, energy loss. System resistance is increased in the suction side, so in the discharge side. So increases vibration and corrosion also. Therefore, it will also reduce the safe operation and increase the maintenance chances. So reduce the lifetime also. So variable speed drives are a better solution than throttling in terms of energy efficient operation. The flow through valve can also be reduced by installing a bypass control system. That is, in the discharge of the pump, if it is divided into two flow channels in two separate pipelines, one is delivering the fluid to the delivery point and another is returning the fluid into the suction side or to the suction store. So in that way, when part of the fluid is pumped back and for no reason, and therefore it is an wastage of energy, so this option should be avoided, which is a type of recirculation arrangement. And this recirculation, initial stage startup, it is essential, but gradually it has to be avoided, and we go for control by variable speed drive. Now recirculation lines are actually essential for large capacity pumps, because for large capacity pumps, particularly where we require a continuous liquid flow to prevent churning, and when discharge valve is closed, we need to a kind of recirculation fully open so that continuous recirculation takes place and that establishes some flow. And gradually, when discharge valve is getting open, then we gradually close the recirculation valve, and that way we regulate it. And minimum recirculation system is incorporated in boiler feed pump as well as in CEP. So these are necessary to start up and priming, otherwise we cannot run the system. Now another method to reduce the energy consumption in pumping system is to reduce the flow rate by starting and stopping the pump whenever necessary, provided that this does not happen too frequently, because 6.6 kV motor, once you are running, immediately you cannot start after a tripping or stopping. So naturally this option is applied when we try to fill a storage tank with constant rate of flow, steady rate, or we have controllers installed for minimum and maximum level, according to which pump starts automatically and stop automatically. So this way it can be incorporated for better management of energy efficient operation. Let us try to understand the arrangement of impeller trimming as a process of energy efficient arrangement. Now changing the impeller diameter gives a proportional change in the impeller peripheral velocity, and as we change the impeller diameter, it is an energy efficient way to control the pump flow rate. So this option should be considered in the sense that it cannot be waste where varying flow pattern exists. The impeller should not be trimmed more than 25% of the original impeller size, otherwise this will lead to vibration and there may be chance of cavitation. So it is very precisely it has to be done. The balance of pump, is maintained, and impeller trimming should be done from the all side, and changing the impeller itself is a better option than trimming sometimes, but we have to see which one is the economic option, and we have to see the effects depending upon the desired performance. So all these things has to be balanced before we choose for going for impeller trimming. If we compare in this table three options to improve energy efficiency in pumps, changing the control valve or trimming the impeller or adopting variable frequency drive, the VFD clearly reduces power most, but it is having high cost. Now, changing control valves should at all times should be avoided because it reduces the flow, but power consumption is not reduced, rather it increases the maintenance cost. So we have to judiciously utilize the services and go for better control arrangement. So that's the end of the brief on pump and pumping system. So I hope I have tried my best to capture all the points within a small span of time. Though there in the pump and pumping system there are several important things which you need to know, and even for pumps you require at least 25 to 30 hours input so that you can understand the basic application of pumps, working principles, how it can be utilized for best performance arrangement. So thank you all. If you have any queries, please mail me, and all the best to all of you.